Okay, Assalamualaikum. We are from Group 5, Session 7, and this is our project for manufacturing process SEMM 2713. Our title is Airplane Nosecone. So in here we have four group members, which is Muhammad Fakrul Razi, Haikal Hakim, myself Adam Shauki, and Muhammad Shazwan. Alright, first introduction. I will go through the introduction. The nose of an airplane is a critical component that influences aerodynamic performance, structural integrity, and functional capabilities, borrowing methodologies from diverse industries, such as the manufacturing of household appliances, provides valuable insights into efficient material selection, design, and production processes. This document integrates principles and practices adapted from gas stove manufacturing to guide the development of airplane nose. So here in the introduction part, we mentioned about what is airplane nose, and next is the method of production. Okay, so there are three method of production, which is prototype manufacturing, batch production, and mass production. All right, so 1.2 is the function of the airplane nose. First one is the components of the airplane nose, which is the radar system, pitot tubes and sensors, and many more. Next is functions of the airplane nose, which is aerodynamic efficiency, housing for navigation system, the impact resistance, structural connection, and environmental control. Alright, so on to 1.3, assumption on the type of manufacturing system. So here, the manufacturing system for the airplane nose integrates three key elements: input, process, and output. Input involves material selection and design planning, while the process transforms raw materials into functional components using advanced techniques like composite layup and machining. The output is a high-quality, tested product ready for integration into aircraft. Efficient planning and execution ensure optimal productivity and adherence to safety standards. Alright, so 1.4 is the assumption on the quantity of production. Airplane nose are typically manufactured in smaller quantities compared to mass produce. This is due to the cost and the size of an airplane. Okay, so basically, airplane is a small quantity of production. As a result, production focuses on precision engineering rather than a high volume output. This low quantity production emphasizes flexibility, enabling manufacturers to adapt to design changes or upgrade seamlessly during the production life cycle. Alright, so by combining this approach, manufacturers achieve a balance between maintaining strict compliances with industry standards and managing the high costs associated with low quantity, high precision, and production. Alright, so the last part is 1.5, product or cost estimation. So in this table, we estimate cost for each part, which is for the first component is composite material such as carbon fiber, epoxy resin, and many more. We estimate it to 150 to 300 per kilogram. Next is metal alloys, which is aluminium or titanium reinforcement, around 200 per kilogram. Labor, which is skilled technicians and engineers, which is around 10,000 to 25,000 per month. And energy consumption, such as power for CNC machinings, autoclaves, and more machines to manufacture our nose cone, which is 5,000 to 10,000 per production cycle. Toolings, which is custom molds, dies, and jigs, 50,000 to 200,000, CNC machines for precision machining, and many more. Alright, so next to 2.0.
Hi, my name is Haikal Hakim Yasradi. So, for 2.0 detailed specification of the final product. First, material selection. The material chosen for the nose of an airplane must meet stringent criteria to ensure performance and safety under extreme conditions. Borrowing from the stove manufacturing process, where cast iron and stainless steel were chosen for their resistance to heat and corrosion. The first one, lightweight strength. Aircraft require material with high strength to weight ratios to maintain. And second one, corrosion resistant. Third one, impact resistant. Common material for airplane nose is first element alloy, carbon fiber reinforced polymer CFRP, titanium alloys. Second, component analysis for airplane nose. Outer shell. The outer shell for airplane nose is a critical component that influences the aircraft aerodynamic, structural integrity, and functionality. Function aerodynamic. Uh, Aerodynamic protection, structural support, material consideration, must be rather transparent to allow electromagnetic. Typically construct from fiberglass composite, quartz composite or reinforced polymer. Key properties: lightweight, height strength to weight ratio, weather resistant, durable against impact and vibration. So this is a figure 2.1 young modulus versus strength. Internal structural support function provide structural integrity to the radome and holds the radar system securely in place. Absorb and distribute mechanical loads such as pressure changes and vibration during flight. Material consideration require high rigidity and strength to support equipment without deformation. Key properties: height stiffness, low thermal expansion, corrosion resistant. Figure 2.2 strength versus maximum service temperature HB chart. Radar system and avionics function. The core purpose of the radar is to house and protect the radar system, which enable navigation, weather detection, and object tracking. Material consideration. Radar components are often constructed from precision engineered metals. Key properties: high electrical conductivity of antenna, heat resistant for electronic, compact and lightweight design. Figure 2.3 thermal conductivity versus electrical resistivity HB chart. Seal and fastener function create a secure and weather-light enclosure to prevent moisture, dust, or contaminants from entering the radome. Ensure the outer shell remains firmly attached to the aircraft structure. Material consideration: seat are typically made from high-performance elastomer or silicone. Fasteners use corrosion-resistant metals like stainless steel or titanium. Key properties: elasticity and sealing capability for gasket, high tensile strength for fastener, weather and chemical resistant. Thermal and EMI shielding function process internal components from extreme temperature and electromagnetic interference EMI. Material consideration: thermal barriers are often ceramic based or use advanced polymer coatings. EMI shielding use conductive coating or embedded metal mesh. Key properties: high heat tolerance, effective EMI attenuation, lightweight design. Surface coating function provide additional protection against UV radiation, environmental wear, and aerodynamic drag. Material consideration: coatings are typically polyurethane based for durability and smoothness. Key properties: UV resistant, hydrophobic, and anti-ice properties. Aerodynamic efficiency. Stage of process. The airplane nose must fulfill several key roles. The first one, aerodynamic efficiency. Second one, structural safety. Third one, sensor and radar housing. Functional measure, cache worthiness, stealing and pressurization. Alternative process, hand layout process. Use case, low volume production, prototyping or custom component. Details, the hand layout process involve manually laying composite material. Advantage: flexible and cost-effective for custom part and small batch. Lower initial investment compared to automated processes. Disadvantage: labor-intensive, leading to inconsistent quality, longer production time compared to the process like RTM or autoclave curing. Resin transfer molding RTM use case: medium to high volume production, particularly for complex and high strength parts such as the radome or outer shell. Details: in RTM, dry fiber are placed in a closed mold. Advantage: high quality finish with consistent result, automated, reducing labor cost and increasing production speed. Less waste due to efficient resin use. Disadvantage: requires specialized mold and equipment, higher initial setup cost compared to handheld up. Additive manufacturing, 3D printing, use case, prototyping, custom part, and small volume production. Details: additive manufacturing use 3D printing technology to build up layers of material. Advantage: capable of producing complex geometry that would be difficult or impossible to achieve with traditional manufacturing methods. Ideal for rapid prototyping and custom design, minimal material waste. Disadvantage: material properties may be inferior to traditional methods, expensive for larger parts, and low volume production.
Okay, I'm Fakrul. I'm gonna explain type of process selected for each step or stage of the total product manufacturing. Okay, these are the stage, selected process and alternative process. Okay, this is a process flowchart of how we how we doing this design and prototyping, material selection, outer shell manufacturing, radome manufacturing, structural frame manufacturing, avionics and sensor integration, surface finishing and coating, final assembly, testing and quality control. Okay, next, engineering application of GD&T and technical growing. Geometric dimensioning and tolerancy. GD&T is a symbolic language used on technical drawings and models to define the allowable variations of parts for fit and function. It provides a clear and precise method for expressing geometric features and tolerances, ensuring that parts fit together properly, perform as intended, and meet quality standards. Importance of GD&T in the airplane nose project is precision and accuracy, fit and function control, tolerance allocation, reducing misunderstanding and errors, cost efficiency. Okay, I'm gonna pass this to Shazwan.
Thank you, Haikal. So now we present the types of machine equipment for each process. So we have five equipments. The first one is composite. We have autoclave. The autoclave process is very critical for the composite components of the aircraft nose. The process initiates with the layer of composite materials, followed by curing under controlled conditions at temperature between 120 to 175 Celsius and pressure up to 6.9 bar. This ensures the proper consolidation and curing of the composite materials, resulting in high strength, drawing components. Okay. So next one is the metal forming equipment. So we use a sheet metal forming machine. This one in the lab, we deal with flat sheets of metal that being turned into curved and complex geometries. Starting from the raw sheet metal, a number of machines are utilized, including press brakes for shaping panels, rolling machines for curvature in sections, and hydraulic presses to perform complex forming. Metal spinning equipment delivers axially symmetric components to either hot or cold spinning operations with particular suitability for aluminum or titanium components. Next one, we have metal cutting equipments. So we have wire EDM and CNC machine. So wire EDM machine use an electrical charge between wire to cut conducting materials. The process involves first programming to cut path and then setting up the workpiece submerged in a dielectric field bath. Its ability to create precise cuts through electrical discharge make wire usually brushed copper, ideally for complex shapes in hard metals, such as titanium. This process is especially useful in making complicated parts with very close tolerance. Then we have CNC machine. This one forms the backbone of aircraft nose manufacturing, utilizing multi-axis machine, which is 3, 4, and 5 axis for complex contours. The input materials typically include aluminum alloys, titanium, and high steel strengths. These machines with a working capacity of 3,200 dimensions produce precision machine structural components with tolerance as tight as 0.05 millimeter. This process involves computer controlled cutting tools that remove material to create the final shape. Then we have casting process. We have two injection molding machines and compression molding machine. The similar with this is to produce a smaller components with precise temperature and pressure, and it involves melting polymer materials and injecting them into molds under pressure. Okay, so next one is chapter 6, which is green manufacturing and sustainability. So green manufacturing and sustainability, green manufacturing in aircraft nose production has transformed significantly through sustainable practice and environmental consciousness. Modern aerospace manufacturing facilities now employ eco-friendly materials and processes, with radome structures utilizing 50 to 53% composite materials like fiberglass and quartz composites for radar transparency, while structural components incorporate recycled aluminum alloys and titanium alloys for high-stress areas. Energy efficiency is achieved through temperature control clean rooms operating at 120 to 165 degrees Celsius and optimized autoclaves with pressure range up to 0.9 bar, alongside smart manufacturing system and renewable energy sources. Waste management has improved through material recycling programs that recover up to 80% of composite waste, closed-loop recycling system for aluminum components, and additive manufacturing implementation. The industry's commitment to sustainability extends to supply chain practices, with major manufacturers like Airbus achieving ISO 40001 certification and Boeing implementing recycling systems that save 10 million kilograms of aluminum annually. These initiatives demonstrate how green manufacturing not only reduces environmental impact but also enhances operational efficiency while maintaining strict aerospace quality standards. So to summarize all from our chapter, so the manufacturing of airplane nose is highly using integrating the advanced engineering, precision manufacturing, and sustainable practices, utilizing lightweight materials like carbon fiber composites and aluminum alloys. The process employs cutting-edge technology, including CAD model, 3D printing, and automated assembly operating at certain temperature and certain pressure for composite curing. Modern facilities implement green manufacturing through recyclable materials and engine engineering process, with company like going again through the cost loop recycling. Key equipment include autoclaves for composite curing, multi-axis CNC machines, and precision metal forming equipment, all contributing to components not meeting strict aerospace standards while maintaining environmental responsibility. So that's it for our group. Thank you very much.
Dah. So, thank you everyone.
Thank
Okay.
you.
Alright.
Right. Yang aku share evaluation.